Well, hello there. I'm going to be working through some of the problems. We'll see how many I do on this Unit 7 additional test review. And I don't have a graphing calculator with me, so some of these problems I'm going to just set up and then let you use a graphing calculator to compute. So let's start with some rate in, rate out questions. It may be that those are the only ones that I'll work through, but let's see what we have time for. Okay, so problem one, from 5 a.m. to 10 a.m., the rate at which vehicles arrive at the Peace Arch border crossing is given by this function a of t, 450 square root of sine 0.62 t. That seems a bit odd. I am guessing that it is supposed to be 450 times the square root of sine of 0.62 t. That's what would make sense. So I think that this parenthesis should be moved to the other side of the t. Okay. Where t is the number of hours after 5 a.m., and A of t is measured in vehicles per hour. Traffic is flowing smoothly at 5 a.m. with no vehicles waiting in line. So since t is the number of hours after 5 a.m., I know that 5 a.m. is going to be t equals 0, and 10 a.m. is going to be t equals 5. So that might be useful for me later. Right, but do not evaluate an integral expression that gives the total number of vehicles that arrive at the Peace Arch from 6 to 10. Okay, so remember that would be t equals 1 to t equals 5. So since I was given the rate at which they arrive, which was right here in vehicles per hour, I should be able to just integrate that to find the total number of vehicles that arrive. So that would be the integral from 1 to 5 of a of t dt. And whatever my calculator gave me for that would be the total number of vehicles that arrive. Find the average value of the rate in vehicles per hour at which vehicles arrive at the Peace Arch. So if I want to find the average value of a function that I have, I am going to use this formula, 1 over b minus a integral from a to b of f of x dx. That finds the average of f. So since I have that function, I have the rate at which they arrive, I am going to use this formula. So 6 a.m. to 10 a.m., again, that's t equals 1 to 5. So that's going to be 1 over 5 minus 1 times the integral from 1 to 5 of a of t dt. Essentially, it's part a divided by 4, because that's going to be 1/4 times the integral from 1 to 5 of a of t dt. That is the average of a. And that's what I want, because I want the average value of the rate at which they arrive. And this is the rate at which vehicles arrive. So I'm finding the average of that function. Okay. Part C, find the average value of the rate of change of the rate at which vehicles arrive at the Peace Arch. Okay, so now I'm trying to find the average value of a prime. Want average of a prime of t, right? Because it's the rate of change of the rate at which vehicles arrive. So I want the rate of change of a of t. So if I had a prime, then I would use my integral formula. But since I have a, I can just go back to semester 1 and say, well, that is just going to be this formula, f of b minus f of a over b minus a. That gives me the average of f prime, right? Because that's the average slope. So in this case, since I want the average of a prime, I can simply do a of 5, right? Minus a of 1 divided by 5 minus 1. So that is the average rate of change of A. And the average rate of change of A is the average of A prime. The average rate of change of A is the average of its derivative. That makes sense, I think. Okay, so two different ways to find average value, right? Because if you find average value of a function that you have, you're going to use your integral. If you want the average value of the rate of change of a function which you have, you're going to find the slope of the secant. Okay, part D. Is the rate at which vehicles arrive at the Peace Arch at 6 a.m. increasing or decreasing? Give a reason for your answer. You'll notice, by the way, that this is really just a rate in problem. There's no real rate out, at least not yet. So is the rate increasing or decreasing? Is the rate increasing or decreasing? So since A is the rate, we want to know. So is A increasing? If we want to know if A is increasing, we want to know if A prime is positive, right? We need to look at A prime and see whether it's positive or negative. So we would need to look at A prime of, remember this is t equals 1, A prime of 1, and see, is it positive or negative? So you could do that on your calculator. If A prime of 1 is positive, then the rate is increasing, meaning more and more cars are coming. If A prime of 1 is negative, then that means the rate at which vehicles arrive is decreasing. Okay. Finally, part E. A line forms whenever A of t is greater than or equal to 400. Okay, let's go back up and just think about what that means. So A of t is the rate at which vehicles arrive in vehicles per hour. So that's basically saying that this Peace Arch border crossing, I doubt this is actually accurate, but can process, well, maybe it is actually, can process 400 vehicles, right, per hour. I don't know if that's true or not, but 400 vehicles per hour is how many they can process. So if the rate at which vehicles are arriving is faster than that, then you're going to start to get a line. Okay, the number of vehicles in line at time t for a is less than or equal to t is less than or equal to 4 is given by the integral from a to t of a of x minus 400 dx. So this is the number, this is now the number of vehicles in line. Number of vehicles in line, where a is the time when a line first begins to form. To the nearest whole number, find the greatest number of vehicles in line at the toll plaza in the time interval a is less than or equal to t is less than or equal to 4. Okay, we are trying to maximize this. Want to maximize this. Okay, on the interval a is less than or equal to t is less than or equal to 4, which is a closed interval, by the way. So that means the closed interval test or the candidates test might apply. So let's see what's going on here. Basically, what we can do is check the endpoints and also check any critical points, right? And critical points would be where n prime of t is equal to 0. Okay, but remember, if n of t is equal to this integral from a to t of a of x minus 400, that means by the second fundamental theorem of calculus that n prime of t is equal to a prime of t minus 400, right? Because if you take the derivative of an integral function, you simply get the function that you were finding area underneath. So n prime of t would be a prime of t minus 400. That's just the derivative of this integral function. That comes from this rule, right? The derivative of the integral from a to x of f of t dt is just f of x. Okay, so that means if we want n prime of t to equal 0, right, then that means we want 0 to equal a prime of t minus 400, which means that a prime of t equals 400. So we basically need a prime of t to equal 400. Now I'm realizing that I made a mistake here, so I got to erase this because n prime should actually just be a of t minus 400. So therefore, if we want that to be equal to 0, we need a of t to equal 400. So what you can do is set a of t equal to 400. Now, once you've set a of t equal to 400, you're going to get some value. Let's say it's t equals, I don't know, 2. It's probably not, but let's just say it's t equals 2. So if it's t equals 2, then you need to look at n of a, which is your first endpoint, n of 2, which is your critical point, and n of 4, which is your other endpoint. So n of a would just be 0 because you'd be integrating from a to a. You need to compare n of 2 and n of 4 and see which one is bigger. Now remember, it's not actually going to be 2. It's going to be some other value that you get by basically solving the equation a of t equals 400. What's important about this whole, let's see if I can actually erase this and go back. What's important about this part of the problem here, this is probably, or definitely the most difficult part, is that you are trying to maximize this function right here. So if you're trying to maximize that function, you need to find its derivative, which is a of t minus 400 by the second fundamental theorem of calculus, and you need to set that equal to 0. When you do that, you're going to get a of t equals 400. This is to find critical points. Okay? Now remember, once you find any critical points, you need to compare the value of your function at the end points and at any critical points that you find by setting the derivative of the function equal to 0, because this is a closed interval, and the largest of those will give you your maximum. Okay, let us move on to problem number 2. Well, here's a true rate in, rate out question. Tide removes sand from Sandy Point Beach at this rate. So this is our removing function. So I'll just put that this is out. Okay, and then it adds sand to the beach using this function right here. So this function is in. Okay. Both RFD and SFD have units of cubic yards per hour. Okay. And T is measured in hours for 0 is less than or equal to T is less than or equal to 6. At time T equals 0, the beach contains 2,500 cubic yards of sand. So that's what we started with. So let's see what we can do. How much sand will the tide remove from the beach during this 6-hour period? So we are going to focus on the out function in this case, right? Because we are removing sand. So we're going to focus on our out function. So that would just simply be the integral from 0 to 6 of r of t dt. And of course, that is going to be in cubic yards. Okay. Write an expression y of t for the total number of cubic yards of sand on the beach at time t. Okay, this is a great problem to do. So remember that you're going to have an integral function because we started with our rates. And essentially what you want to have is what you started with, starting amount, okay, plus the integral of the in rate minus the integral of the out rate, right? That's essentially what we are going to do to get our function for y of t. Okay, so y of t, what was our starting amount? Our starting amount was 2,500 cubic yards of sand. Now we need to integrate, and we need to integrate with an upper bound of t because that is our variable. So we always want to have our upper bound of whatever this variable is. In this case, it's t. And our lower bound will be when time starts, which is t equals 0. And then our in rate was s of t. Okay, and they both started at 0, so we can do s of t dt. And then I can subtract the integral from 0 to t again, because t is our variable, and we started at 0, of r of t dt. And that would be an expression for y of t. Now, if we wanted to, we could simplify this since they both have the same limits of integration, right? They both start at 0 and they both go to t. We could combine that into one integral, and that might be preferable. So we could write y of t is equal to the starting amount, 2,500, plus the integral from 0 to t of s of t minus r of, it really shouldn't be t here, I'm realizing, because it should be a different variable than the t. So we could say s of x minus r of x dx. We just want a different variable so that we can plug t in. So let's go back and change these to r of x, s of x dx, and r of x dx. You could also do s of u du and r of u du. You just want that variable to be different than t, which is the variable that's going to get plugged in. Okay. Find the rate at which the total amount of sand on the beach is changing at time t equals 4. So that is basically y prime of 4, right? And if I take the derivative, I just need to remember my second fundamental theorem of calculus. If I take the derivative of y of t, of course, this guy is going to be gone because it's a constant. And then remember, if I take the derivative of an integral function, I just get the integrand function. So I'm going to end up with s of t minus r of t, which is what I know from the very beginning, right? If I take my in rate and subtract my out rate, that should give me the rate at which the total amount of sand on the beach is changing. So I guess to make this precise, I have just found y of t. So if I wanted to solve this, I would need to find y of 4, which is s of 4 minus r of 4. Okay, for 0 is less than or equal to t is less than or equal to 6, at what time t is the amount of sand on the beach a minimum? Okay, so we are trying to minimize y of t. So that means we need to find y prime of t and set it equal to 0. And since we have, again, a closed interval, we need to use the closed interval test, sometimes called the candidate's test. We need to find y of 0. We need to find y of 6. And we need to find y of any critical points that we found by solving this equation. To find critical points, right? So that is the closed interval test. So anytime you want to minimize or maximize a function on a closed interval, you need to compare the endpoints. Right, this is a review from last semester. Endpoints, and you need to look at the critical points. So critical points. You need to evaluate the function at each of your endpoints and evaluate the function at your critical points to decide which one is the largest, or in this case, which one is the smallest. Okay, so I hope that is helpful when you're thinking about problems related to linear